This is actually lesson 7, projectile motion. So I want you to understand a projectile is anything that can be thrown or shot, fired like a missile, throw a football, hit a golf ball, toss a ball with your friend. Anything that's shot or thrown like that is considered a projectile. So it all falls into this idea of projectile motion. Quadratic equations will tell you the position at all time. It will tell you how high it is at any given time. Let me say that again. It will tell you the height at any given time. Guess what 2 letters are in the equation? T and H. Height and time. Height and what else? Time. Awesome. It does. So we have touched on this. We have done some things in Math 1 that's going to be helpful here. Okay, when you were in Math 1, you probably saw this equation before. I want to focus in on this. Let's first of all focus in on this. Do you see t squared? Do you see t? Do you see no t? Is this what we call descending powers of t? T to the second power, t to the first power, no t at all, or t to the 0 power. Everybody good with that? The next thing is what you really need to focus on. Okay. Negative 16. Would you put a circle around negative 16 right now? Find the big dark black box and circle negative 16. That's a very key number. Where does negative 16 come from? Well, you might want to know, or you might be interested to know, or you may not. But anyway, I'll share with you. Miss Jessup is a math science teacher. So I taught physics for a number of years. So I love this equation. I love this particular lesson. And so it comes from the physics formula that has negative 1/2 g t squared. Take a wig wild hairy guess what g stands for. Gravity. Gravity is one of those things that it's a force that pulls everything to the center of the mass, which in our case is the center of the earth. But gravity doesn't take a vacation, does it? So if I jump off of a 2-story building, I'm going to smack to earth because gravity's pulling me down. Tomorrow, gravity's not going to go on vacation and not be working, and I can just jump off and never hit. Or one day, I won't jump off and gravity pull me really fast, and the next day it pulls me less. It's not how gravity works. So because gravity is so incredibly consistent, and praise the Lord that it is while we're living, otherwise our planet would probably tear itself apart, gravity's always going to be the same. In the English system, which is what we use, y'all realize we use the English system. We use inches, feet. We still measure in pounds. Everybody good? Turns out gravity's number is a consistent number, 32. What's half of 32? 16. Hence, guess what number shows up in our equation? Negative 16. Is it ever going to be negative 15? No. Is it ever going to change negative 2? No. If it is, that's a different gravitational constant, maybe on a different planet. Moon's gravity is not the same as ours because the moon is smaller than the Earth. Everybody good? Okay, and the other planet, if they're bigger than us, they have stronger gravity. If they're smaller than us, they have weaker gravity because gravity is consistent with mass. That's right, keeps us all in our orbit. So here we go. The numbers that will change. Next number. Circle this number. The next number that will change is the number in front of t. It's considered V sub 0. What does sub 0 mean, do you think? Okay, the subscript 0 is below the line. When a ball is thrown, when I'm throwing it, do you think it has the same velocity every second, or does it change? It changes. So V sub 0 would be its velocity at 0 time, which would be its start velocity, right? So immediately if I throw it, the second it leaves my hand, however fast I'm throwing it, that's its initial speed. As soon as it leaves my hand, though, air resistance and gravity is going to change it, right? It may go up, then it's going to go back down. Does that make sense? So your velocity is going to change. So this is your start velocity. Start. Oh, it's right here. Start or initial velocity. The number in front of t is your start velocity. Okay. The number at the end, no t. Y'all remember that number at the end, that is your y-intercept? It's your h sub 0. If you throw a ball, does its height change? So it's its height at 0 time. Sub 0. Height at 0 time, which is its start height. So this number at the end is very, very helpful because it'll tell me how high I started. So, having said that, let's just jump into some problems. We'll be coming back and you'll be having to figure out, why is this number important? Why is that number important? Guess what number is not going to change? The negative 16. Oh, I forgot to ask this question. Why is it always negative 16? Why isn't it just 16? Why is it negative? Huh? Gravity pulls us down. Gravity's never going to just push us up. I've never been standing around all of a sudden just get lifted in the air. Gravity doesn't push you up. It always pulls you down. So that's why it's always going to be 16. It's always negative 16. Everybody good? You have to remember that. So this version of the standard form of the equation, that's the standard form. Everything's multiplied out. There's no parentheses. All right, let's jump in and do number 1. Or excuse me, this is continuation from yesterday. This is actually number 4. What's missing at the tip top? No questions. Which means we get to ask the questions. Yay! Which means we get to kind of sort of pretend and make up our own scenario about what's going on. We do have inspiration. I do see this playful little squirrel sitting over here on the tree. Y'all see the little squirrel? Yay. Okay. I have no equations at all. I have no questions. But I do have what? What did they give me? They gave me some data table information, right? They told me this is my time in seconds. And they told me this is what? Height of acorn. That's a clue. So I got a squirrel picture, and they talked about height of an acorn. Okay, let's move on. Best thing we can do is what? We do not really need, that used to be where we had workspace, so we don't really need to worry about workspace. We can just use our data tables and stuff. But we can do what? Can we change the data points into graph points? Let's do that. Let's go -2 up 0 height. Let's do that right now. -2 up 0 height. Put your point on there. -2 up 0 height. -1 up 48 height. -1 up 48 height. Got that point on there? Go over to 0 up 64 height. Over 1 up to 48. And over 2 up 0 height. I think I have enough points that I can sketch a pretty decent picture of the path of these points. Real world problems. We get to come up with a scenario. Can anybody think of, and there's actually a few different kinds of questions we could ask. So we got a picture of a squirrel, and we've got data that says something about height of an acorn. Wonder what I could possibly have as a question. Wonder what happened here. Anybody kind of put their thinking caps on and figure out a scenario that involves a squirrel and an acorn and Ice Age, inspiration, okay. Yeah, I remember that. That's hilarious. Ice Age.
That is maybe where you would see a squirrel throwing an acorn, a limb that is a certain height off the ground to another.
Yep. All right. I want to do something right here, right now. Got your pencil or your pen? If this is a real world situation, does it make sense to talk about -2 time and -1 time? No. So right now, take your pen or pencil. I want to basically realize we're going to cross out We do not really have to consider that side of the graph. That would never be anything we would actually be talking about in the real world situation of this squirrel and this acorn. Okay? Got a question for you. Okay, anybody thinks they know what happens here? We've already talked about, what's a question we could ask? Somebody come up with a question. Does it increase or decrease? That's a good question. Is the graph increasing or decreasing? Decreasing. Is this graph ever increasing in the real world? No. So it looks like this acorn is only ever falling, right? Good question. Good observation. High five on that. Another question. Different question. Do we know how high in the tree the acorn must have been? Okay, is that a question? And we have an answer, right? Okay. We have, is it increasing or decreasing? Let's write these down. Okay, it is decreasing. That's our answer. This is the first question. I did ask a question. I pushed you. I prodded you. Everybody ready? I asked what? How high is the acorn? What's the answer to that question? 64 feet. Everybody knows how we got 64 feet? Guys, there's another question. What else? Oh, let's go back and look at the graph. When this squirrel and did this acorn leave the tree with any extra velocity or any velocity? Like, I'm imagining if I was standing up on top of a hill, or if I was in the tree and I was going to throw an acorn, I might throw it, and instead of just going boop, it would probably go what? Up and down. Does that make sense? Did this acorn leave the tree with any extra velocity of its own? No. Does everybody agree with that? I don't think it did. I think this acorn just like fell out of the tree. Does that make sense? That's the story I'm getting from the data. Otherwise, I think it would have went up and then come back down. Do y'all agree with that? So we're going to say has zero initial start speed. Do y'all like the word initial or start? Start. So that's my start velocity. Everybody agree with that? I'm ready to write an equation. Let's write an equation. You ready? Let's go back and refresh real fast. Here's my equation. Guess what number is always going to be in it? Negative 16. And it's going to be with the t square. There's going to be a number in the middle with t. And there's going to be a number at the end. Y'all ready? So there's two numbers that we usually have to do ourselves. All right, here we go. Standard form. H equals. What number did you say was always the same? Negative 16, because that's gravity. And that's in front of t squared. Plus, how fast did we say this acorn was flying out of this tree? How fast did we say it was flying out? 0. Did we all agree it had 0? I think this acorn was just sitting there doing nothing and it just fell. And then plus, how high was it? 64. So one more time. This is its start speed or velocity. And this is its what? This is its start height. By the way, do you have to keep the 0t in there? So could this actually become h equals negative 16t squared plus 64? Wouldn't that be the version of the equation we would work with? We wouldn't bother putting 0t in our calculators, would we? No. Everybody good? By the way, that is factored form. What is the vertex of this parabola? Over how many? Over 0, up 64. So that's 0, 64. And if I did 0, 64 as my vertex, wouldn't it be h equals negative 16 t minus 0 plus 64. That would be the vertex form. I think I forgot to type that in here on my paper. Factored form. How do I get factored form from my graph?
So anytime we're doing this kind of problem, we just, that negative, that 16 is before the parentheses.
As long as they're in English units. Otherwise, they will supply you with an acceleration. You will never have to come up with that on your own. Factored form. All right, ready? H equals 2 sets of parentheses, t and t. All right. Where do we look to get numbers to go in factored form? Where it crosses the vertex. Nope, not vertex. We already got vertex form. That was different. I need the what? We need the x-intercepts. Basically, where is it on the ground? So I don't really need the left half for the real world situation, but I kind of sort of need it to help me with this. It crosses the ground, right, at 0, x-axis, at -2. I don't put -2 in my equation. It's supposed to go in as what? Opposite, so +2. It also crosses the x-axis where else? Does it cross at +2? But it goes in my equation as -2. What is Miss Jessup forgetting in the very front? -16. Okay. So do we have factored form, standard form, and vertex? All right. And we've asked the question, how high is the acorn? What else can we ask? Okay, acorn, are you ready? Woo! Hits the ground, right? Is there another question I could ask about how it hits the ground? When does it hit the ground? Thank you, thank you. When? It's a big question. When does it hit the ground? 2 seconds. How do you know it's 2 seconds? Guys, anytime it talks about hitting the ground, you're always down here. This is where it hits the ground. You're looking at where it crosses or touches the x-axis. If it says, when does this hit the ground, always go to the x-axis and just hit that point. Everybody okay with this one? Let's go. We got 2 more to go. Move. Let's move, let's move, let's move. Ma'am. Number 5. Different question. What do I have? One equation. Everybody got that? One equation. No question. We do have an inspiration photo. Fireworks. Can we get that? Okay. No data table. No graph. So, where do I start? Start with factored form, right? What information can you get from factored form immediately? Well, I could get standard form. I can multiply it out. Y'all want to do that? Okay, here we go. That was not where I started, but you're good. That was good. Ignore the -16. So y'all better have a calculator because these numbers are going to get bigger. You ready? Okay, -16. I need to multiply these two first. What's t times t? T squared. T times +1. +1t. -32 times t. -32t. -32 times +1. -32. You need to be writing this down. You need to write this down. What does that simplify into? What does +1 minus 32 give us? +1 good guys battling with 32 negative bad guys. Who wins? It'd be -31t. Okay. Now that whole mess gets multiplied by -16. There I have a calculator or use DESMOS. Y'all ready? What's -16 times t squared? -16 t squared. What's -16 times -32? No, -31. -16 times -31. Use DESMOS or calculator, whatever you got. Who's got it? -16 times -31. 496 plus 496, that number has meaning, T. And what's negative 16 times negative 32? Negative 16 times negative 32. 512. Oh, that number has meaning. We just learned a whole lot. That actually was a pretty good strategy. Yeah, let's go to standard form. Yay. What do I know? I can already ask some questions just from the equation. Who's got one question for me? Ding, 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 ding. Oh, I love you. Where's my candy? I'll go get it. What is the height that the fireworks were displayed from? Yeah, let's write that down. Let me ask you a question. If you ever went to a fireworks display, where do they normally take the fireworks to shoot them off? They don't go in the ground in the lowest little hole they can find, right? Don't they go from a hill or top of a big building or cliff somewhere? Chocolate or chocolate? Give you a big piece. All right. How high? Good question. How high were the fireworks launched? When we shot them off, how high were they? What's the answer to that question? 500 and, because that's the start height. So I'm imagining that we're up on this tall hill above the town, or on this big cliff above the town, and we're all sitting here in our cars just waiting for the dark to come so we can watch the fireworks. Luckily, I will not have my little dog with me because he hates them. Like scared to death. Anybody got a dog scared of fireworks? Mine. Mine's petrified. Next. We were at the lake once, and they were shooting off fireworks. And we had my sister and her brother, they decided to go to town and get away because he's like just trembles. Terrible. Another question. Anybody else got another question from the equation? Increase or decrease? Good question. And that's not an easy one to answer. Does this increase or decrease? We're going to have more info. And we'll get back to that question. What else can we find just from the equation? Y'all use 512. What about the other number? Yeah, what does that mean? Okay, guys, let me ask you a question. Do you think this is like the acorn? Do you think that they're just going to launch straight down off the hill? We go to a hill, but then what do? We're going to launch them on up from there. So that relates to Nathan's question, which is excellent. Does these just drop straight off the hill down toward us? Hopefully not. Or are these things going to go up and then explode? They're going to go up. So they are going to what? They're going to increase off somewhere off the cliff. Then they're going to come down. That's what I would think. How fast are they moving when they're launched? Ding, 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 ding. How fast are they moving when they're launched? And that answer is 496. I don't know if that's feet per second. I'm going to say it's feet per second because 32 is in feet. Excellent question. Excellent observation. I just love you guys. Okay. I'm going to go back to factored form for real quick. There are 2 points that I can graph really easy just by looking at this. What are 2 points I can graph really easy just by looking at that? The numbers in the parentheses are important. Put your thinking caps on, remember. They come out, but they don't come out the same as. Come out opposite. So they're going to come out at what? 32 and -1. Now, and they come out and they my x-intercepts, aren't they? So that means that I'm going to touch the ground at -1, which is barely over here, and at +32. Everybody good? Since those 2 points I know are going to be the start points on the ground, I know I probably need to put those in my graph. -1, and somewhere I need +32. So far, so good? Okay. Now, I'm going to have to eventually go to DESMOS, right, to see a full picture. I need some points to graph. I need to know how high they go. Anybody wondering how high they're going to get in the sky? Listen to me. If we're talking about exploding pieces of like gunpowder and colorful elements and bits of shrapnel, I'm praying that they explode feet above me, right? Like if they explode 100 feet from me, I could get hit with something. Are y'all with me? Did y'all realize that? What goes up has to come down. Even if it explodes into bits, the bits are going to come down somewhere. How many seconds does it take for those bits to fall? We don't even have to guess. Somebody in here should be smart enough to figure out from what we've seen so far, how long is it going to take these pieces to fall back to the ground? 32. Yep, okay. How high did we say these things are? By the way, time 0 is important because that's really where our real world situation starts. You have to have time 0. And then I need one more important point. So let's just go straight right now to DESMOS. Clear. And I think it was negative 16 parentheses x plus 1 parenthesis closed. Crap. And then x minus 32. X minus 32. And I put an extra subtraction there. Okay. Oh! Hey, imagine that. My numbers from a while ago are still good. That's actually not a bad picture. So, I do need another data point. What other data point do you think is important? Guys? So we clicked on these important points and we figured out that we actually have 4 points that are important, and the highest point is always needs to be included in our list, and that turned out to be 15.5. So at negative 1, we're on the ground, that's 0. Now remember, 0 means on the what? On the ground. At 0, we were what? 512. Was that our start height? Okay. 15.5, how high were we? That's a big number. I don't remember what it was. 4,356. Would that be our max height? Okay, what's 32? Where were we at 32? Where were we at 32? 0, because we were back on the what? Ground. By the way, these are all height numbers in Y, and these are all what? Time numbers. It's always time and height. You got to know what you're looking at. I now have enough points to graph it. So 0, a little bit above there. At 15 and a half, I'm going to be way up here above 4,000. And then I'm back on the ground. So I think I got enough points to at least sketch the graph. So I got my own picture. Everybody good? What's your practical domain? Well, negative 1 is technically on my graph, but is negative 1 in my practical domain? Can you start the clock at negative 1? Boy, I wish I could go back in time, don't you? Sometimes we wish we'd go back and make different decisions. So time. So where does my practical time clock start? 0. 0. And when does it technically end for this problem? 32. At 32 seconds, we're on the ground. If we are at 33 seconds and we're still recording it, this thing is digging its way down in the dirt, right? It could be some kind of missile that just digs its way down, but we don't have any like that I know of. So 32 is when we're stopping our clock, equals. What's our practical range? Height is at H, backwards. How low did it go to how high did it go? 0, because it did come back to the ground. And it went up to 4356 equals. I hope that these are getting easier and easier. So what? Means, is it actually touching this point at 0? Is it actually touching here? Yeah. Okay. So there were some other questions. How How long to hit the ground? How long to hit the ground? 32 seconds. Oh, how high? How high did they go? 43.56 feet. How long does it take to get there? There's a bunch of questions. How long does it take to get there? How long does it take to get to 4,356 feet? Are you having to do math calculations a lot on these? Do you understand what I'm trying to show you? The graph data, the picture of the graph, the questions they could potentially ask you. There's a bunch of questions, so it's not giving us everything. All right, one more, and we'll stop for the day. One more. All right, last question. Jacob is a real fella. I mean, real good guy, you think. He's your buddy. Jacob's your buddy. But Jacob is throwing water balloons at his friends using a water balloon launcher. What a good guy he is. Jacob calculates that the water balloons are traveling at a velocity of 16 feet per second when he launches them. I don't know if he's got like a, I'm thinking, does he have like a slingshot up on this building or what? And he's standing on top of a 96-foot tall building. What a guy he is. I wish I was one of his. I wish I wasn't one of his friends, so that when I'm walking by, he's not targeting me. It's kind of like, y'all ever rode those rides? They're like water rides, and people can actually pay money. Where was this at? I don't know, and they shoot water at you. Okay, they could shoot water at you, but I think the water thing I saw, it kind of went up and over. It's kind of the same deal. So they're launching. So he's launching water balloons at his buddies. What a nice guy. Okay, I have no equations yet. I have nothing in my data table. Well, I don't even have a graph. So guess what? They gave us a couple of numbers in our description. Wonder if we can figure out how to make the equation. We can. It ain't no solution, I promise you. Okay, are we going to do factored form, vertex form, or standard form? Actually, we're only going to do factored and standard. Standard, here we go. H equals. What's the first number that never changes ever, ever, ever? Negative 16. And that's in front of t squared. Got that? Plus, something is in front of t, plus. Now, you got two numbers. Which one's which? The middle one's what? Got to go back and look. Look at your notes. Go back to the other sheet and look at your notes if you need to. Yeah, but is this my start height or is that my start velocity? Velocity. So which number is my velocity? 16 or 96? Velocity of 16. So 16 goes where? Right here. You've got to be able to figure out that for yourself. Everybody good? Everybody see what I'm saying? How high was these when we were launching the balloons? 96 feet. So this is my height. This is my start height. So they are not going to always hand you the equation, but they are going to hand you enough information that you can figure out the equation. Now, do you know where to do? Okay. In my table, it's going to be what? Time is on the x-axis, and what's the other thing? Height. Projectile motion, good thing about it, it's always time and height, time and height, time and height. They gave me a data table that I could put as many points as I need to in there, and they've got a graph, which Miss Jessup has been so kind as to put numbers on for you. So, my suggestion is, go look at it on the graph, find 4 or 5 data points, and tell me what they are. Go right now to DESMOS. Look at DESMOS. Type this into DESMOS. You have one equation. See if you can figure out some key points. I'm going to say where it hits the ground, there should be 2 key points. When it's at the top, what is a key point? At 0 time, that should be a key point. Click a bunch of points. Y'all got at least 4? There should be at least 4 points. So, negative 16 x squared. Are you typing this in? Okay. If you don't want to, I'm not gonna. X plus 96. Oh, I am way off. Okay. See if I can figure out how high it goes. Oh, I think I know how high it goes. Okay, I am going to change it. I'm going to change my screen. Ooh, I don't need that many seconds. I'm going to say within 10 seconds that sucker's back. And I know it goes at least as high as 100. Oh, I don't even need that. See, 5 seconds. Oh. Okay. All right, Miss Jessup changed my window so I could at least see a graph. Have you clicked some points? Click, 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 click. Have you clicked 4 points? Somebody in here should already be able to tell me, when does this hit the ground? When do these water balloons hit the ground? How long is it going to take before they hit the ground? 3 seconds. Make sure you typed it in exactly the same. Negative 16. Did you say plus 96?
Yeah.
16 plus 16x.
Yeah, it's in there. It's just like.
Oh, they are. You've got everything.
Do we use the table instead of just looking up the points?
Here's the thing. Your data, your table just plots points, but it doesn't do half points unless you put in 0.5 by yourself. And that's where, when I just typed it in, out the table, I wouldn't go to the table unless there's not enough points to tap on. So you may have to retype it back in. Okay, let's finish this up. Here's what I need you to do. What are 4 points? What are 4 points? What are they? Negative 2, 0, 3's last, and 0.5. Those would be my 4 key points that I click, click, click across the graph. At negative 2, I'm what? 0, which means technically, does my graph really exist at negative 2? No, but it is helpful to at least see it. Negative 2. At 0, I am how tall? What was it? 0 what? 96, which would be my start what? My start height. So at 0, I was 96. At 0.5 seconds, half a second after he launched his balloon, how high did it go? 100. So that would be 0.5 would be that next line. So right here's 100. And then by 3 seconds, we're what? Back on the ground. Let me ask you a question. What part of this graph do I really not need? In the real world, I do not need the negative side. My graph really starts right here. Everybody good? My graph really starts right there. Because at 3 seconds, I'm back at what? 0, which means I'm on the ground. 0 doesn't mean on the ground. Practical domain. Time in the middle, less than, less than. What is the time that makes sense? Negatives don't make sense. So between 0 seconds on the stop clock, and when we stopped counting? 3 seconds because it's back. 0 to 3 equals equals. As it touches at 0, it touches at 3. Practical range. Lowest to highest. Well, when it's on the ground, it was at 0. Height, between, equals equals. How high did it go? 100. What are some possible questions? Do you now know some questions? One more thing. Tell me the factored form, and you're not leaving until you tell me. Yep. H equals, parentheses, T and T. You got a graph. Look right here. Somebody will be able to tell me in about 2 seconds. Negative 2 goes in as positive 2. Positive 3 goes in as negative 3. So the graph is helpful to write the factored form, but otherwise you only need from 0 forward. So this is going to be, what else do we need in my equation?
Negative 16.
Negative 16.